Hello, thank you. Welcome to my presentation. Let's get started. When I saw this call for paper, there was a lot of interest in the C++ community, at least, about how to write code in another language than C++, which is still fully compatible with existing C++ code bases. So, for example, Chandler Caruth introduced a language called Carbon, which is apparently developed at Google, which will be fully compatible with C++, but better in so many ways, which are not yet defined. So there's just a language specification, which is not that full-featured yet, but they're working on it, so I'm really interested in that language. A bit later, Herb Sutter came forward with basically a way back to into the history of C++. C++ started as C-front, a front end that converted the new language into C code. And Herb Sutter had a CPP front, which converts a new language into C++ code. Again, having a nicer language and still being fully compatible with C++. So we on the other side here, we do have a nice language, at least I think so. So I was interested, how can we actually interact with C++ code bases that exist out there? So Rust was originally developed at Mozilla. Mozilla is a company with a huge C++ code base. So they actually developed it with intention to write code for Mozilla in a safer way. So there was some idea about integration of C++ and Rust from the very beginning. So I want to introduce some ways that can be done, and let me get started with a few words about me. I'm a long-time C++ developer. I have spent like 20 years of my life working with C++, developing UI code, working with UI code, building tooling for languages, and I was, oops, wrong direction. I'm now a Rust developer, and I work on a project I find really interesting, which I'm going to tell you about now. And that's a toolkit written and implemented in Rust. So we are scalable. It runs from a microcontroller like this here, or a picture on the board, up to graphics accelerated workstations. And it's 100% Rust. So why are we interested in C++, you ask? So for two reasons. First off, we also want to provide an interface for C++ developers. We provide a toolkit it's basically language neutral, and it would be really cool if different languages could use it. And one of the languages we want to support is C++. So we have the challenge of integrating our existing Rust code and providing a nice API for C++ developers to work with it. On the other hand, we optionally use existing C++ code. There's really good UI development toolkits for C++ out there, and we want to reuse some of the code they have for our stuff to basically do platform integration into accessibility frameworks, get the styling right, and all that stuff. It's optionally. It's not the final solution, of course. We need something that's fully implemented in Rust, but at the moment, it's a good solution to give us a lot of head start. So that's what we're currently using. So I'm interested in both directions, basically using C++ from Rust and also exposing Rust code and providing a nice C++ interface for it. I have planned to talk about two things, basically code level integration. I have some C++ code, I have some Rust code. How can I make those two talk to each other? And I also have prepared some slides about the build system integration. Because once you have code in Rust and in C++, you need to build it into some combined product. How can you do that? They're interested in that topic, or should I just skip it for the... Okay, I'll try to leave room for it. Thank you. Oops. What do I do now? My window closed. Okay, so let's get started with the code level. So we have two languages. Why is it challenging to integrate them with one another? So first off, Rust has no defined ABI. ABI is basically when you program code, you define functions, you define data types, and the compiler processes that and produces a binary out of that. And this binary has also some kind of interface to assess these functions and methods and data types. And the Rust compiler basically does not define how that looks like. That makes it interesting to have one binary talk to another binary. But on the other side, C++ doesn't either. So they do have compiler. It's basically compiler defined there as well. They, of course, have lots more compilers than we do. So in my opinion, that does not really improve the situation. Then we have two languages with very different concepts. So we have inheritance and multiple inheritance in C++, which is something we don't really do on the Rust side. We have traits, they don't have that. We have lifetimes, they don't have that, but they have templates, which can also be quite challenging. So it's very different concepts, and it's hard to map those on top of each other. And we have another problem. So we have data types. So even if we have the same data types, let's say we have some vector, which is basically in all languages just some memory, a capacity, and a length, you can still have problems communicating this data structure across language binaries because they might define the sequence in which those this data is defined in the structure differently. So Rust side expects to read the length, the C++ side puts the capacity there, the whole thing blows up. The data types might mismatch, so there's a lot of details here. And even if the data types would match exactly, you can still have problems. Think about strings. In Rust, we have a string, which is UTF-8 sequence of characters. C++ has a string, which is a sequence of bytes, which may or may not be in UTF-8. And the programmer knows what he's doing, so he will know which encoding that is. So it's really challenging to mix these two languages. We do have one, basically the least common denominator, and that's basically the C language interface. That's not really that well defined either, but it's the basis of a lot of definitions for binary formats that then use like ELF or PE on Windows, so that it can be used as some common basis that both sides can agree on. And indeed, the C foreign function interface, as it's called, is the backbone of all the different approaches I'm going to introduce today. So how can we generate bindings? So why do we need bindings? Let's start with that. So we have some function in the C++ method. We want to call it from the Rust side. So we need a bit of code to tell the Rust compiler that this function exists, and this is a binding. So we need a way to generate those. The best approach for all the people involved is, of course, having that done automatically. Ooh. So we have several tools for these. There's BindGen, which takes C and simple C++ code and produces Rust files out of that can then call these functions. BindGen is a wonderful tool. It works really well, except there's some construct that it doesn't support. So if there's some multiple inheritance, it can be tricky. And the tool is basically designed to skip over anything it doesn't know and just ignore that part. So when you use it in practice, you will need to tweak it a bit and define the configuration. So it's not fully automatic, but it does get you a long way already. The other direction can be covered by CBindGen, which takes Rust and produces C and C++ headers. This works actually reliably well, and that's because it only looks at functions and data structures you have marked up as Rust programmer with wrapper C. So basically, you made sure this thing can be expressed in the C foreign function interface. So it's really easy to extract that and produce basically C code out of that. Well, that works really well. So the next approach I want to introduce is basically semi-automatic bindings. So the first approach we had, the full automatic one, is basically ideal when you have header files and just need a quick way to get started with those in Rust. This approach is more for people designing a new library, for example, where they basically The idea here is to define the data types and the functions that can be called from one side on the other side, and generate bindings for both sides, and basically automatically generates the FFI interface in between in a way that you don't really need to worry about it. So here, the prominent example is a CXX crate. But there are, of course, other crates that build on top of CXX. There's crates that handle special C++ dialects or whatever. There's extensions to CXX, but this is just the basis here. How does this work? So it takes some Rust code here, and you need to introduce a new module. In this case, it's called FFI, and you mark it up with a CXX bridge macro. This basically tells CXX Crate to take over and interpret all the other code that follows here. And then you can go ahead and describe common data structures. So in this case, the data structure metadata will be available from both sides. Both Rust and C++ will know about it. They can both interact with it. You then can also basically define what you expose from the Rust side by marking it extern Rust. These are, in this case, the exported data type is a multibuf. In this case, it's also just an opaque type. So you can pass it through C++, you can pass a pointer to it or whatever, and you can pass it back into Rust, and the Rust side can then access it again, but you cannot do anything on the C++ side with that. The CXX crate is actually so intelligent that it recognizes that next chunk takes the multibuf as a first argument and actually turns that into a member function, so it's really neat there. Then you can go ahead and define the C++ side. So this is our functionality that's exposed from the C++ side to the Rust side. Here we have a client. Again, it's an opaque type, which cannot be accessed from the Rust side. And the interesting thing here is that you're encouraged to mark up the things that are relevant to the Rust programmer or the Rust compiler, like is this function safe or unsafe to call? Is there a lifetime on the different reference paths and all this? Which is completely ignored by the C++ side. Because these concepts just don't exist there, but they make it easier to work with the data on the Rust side. So with this, you can generate bindings for both languages and start to use them. And the CXX crate here tries to be safe and fast. Safe in this context is a typical Rust safe. So the Rust compiler has checked out the code and is sure that all the invariants it expects from it are held. Of course, that cannot be said about any C++ code simply because the Rust compiler can't understand it, so it cannot uphold any invariants there. So the safe in the CXX crate only applies to the binaries it generates themselves. So that will not introduce any additional unsafety. There's nothing said about the C++ code itself. So you still have to review that as any other C++ code, and it's still have to treat it as unsafe in Rust. The fast thing means that the CXX crate will not do any conversions. So it will do zero copy between the C++ side and the Rust side. This also means that the data types from one side will shine through on the other side. For example, if you take a C++ string and pass it to Rust, on the Rust side you will have a CXX string, because a string in Rust needs to be UTF-8 encoded, and some guarantees need to be upheld, which are not guaranteed on the C++ side. And if you don't want to transcode and copy things, you have to do it that way. So the next approach I want to introduce is basically no binding, and I'm cheating here a bit. The idea is, can you actually write Rust code and include C++ code in there? The fun thing is, yeah, we have the CPP Crate. You can. And this totally blew my mind when I saw that the first time. So you have a Rust function taking a self object, a reference to self, generate a Rust variable object, which takes something out of that self, and then, oops, what did I do here? And then you do this. What this code does is internally it adds a function call, which generates a binding to C++. It generates a C++ function, which takes object as an object pointer, and it generates the code. It compiles that, and then it adds the code you write there into that function, and it compiles the C++ code, generates the bindings for the Rust code, and puts it in place of the CPP macro. When I first saw that, it sort of, mine exploded. So, and you can go one step further. Of course, you can have a Rust macro in there, a pseudo macro, which allows you to switch back into the Rust world. And again, so you have the C++ data type, which is void pointer on the right side, and the Rust data type on the left side. That will be also mapped. This crate is not fully safe, so if these types are not aligned properly, it can crash. Work can be done to improve that, but it's not as safe as the CXX crate. But when I first saw code like this, I was totally blown away. The Rust macro system is so great. So let me summarize the approaches I wanted to introduce to you. So we have several options. So you can use code generators, or you can use macros. If you want to work with a library, you can a C++ library and call code in there. You can also go with a CPP Crate and basically avoid the bindings. Of course, you also need to define data types and everything to make it, if you want to use them from both sides, and there are more macros in the CPP Crate to help with that. But if you want to use a library, you can use the CPP Crate. If you want to write codes that integrates both sides, you have the CXX Crate as a great option. And you can always fall back to code generators like the BindGen or CBindGen and others to generate more code. None of the options we have are fully automatic, so you will need to do some work, especially if you want to have really great and native interfaces. So in Slint, we use BindGen, we use the CPP Crate, and we also have headers, C++ code on top of the generated bindings to make that really nice to interact with. But the cool thing about this, nothing in the Rust language is concerned with C++ compatibility. So we have a language which we can develop completely independent of any types or influence from the C++ language, and we can basically go a completely direct way, independent way. All we need is external code generators like BindGen or CBindGen, and macros, of course. So that's what I wanted to say about there's the code side. Any questions so far? I don't see any. So we stick with the usual format and do it at the end. So let's look at build system integration. That's actually a challenging topic. Usually you will end up with one build system that you have to integrate in another build system. That's for two reasons. Any real-life project and any non-trivial project will have a build system that's just too much work to re-implement in a different way just to build it in a weird setup with some other language. So you will need to embed one build system in another. For the Rust code, that's especially true, mostly because Cargo is the interface to build Rust code that users are expected to use. So that makes it a bit challenging with C++ build systems, which kind of have this approach of running compilers directly, which is something we basically discourage people to do in the Rust world. So in most cases, you will end up with one build system integrated in another one. So let's get started. Oops, that was the wrong direction again. Am I? let's get started with cargo. This is a good approach if you have a little C++ code that you want to integrate in a cargo project. If you go for that approach, first thing I recommend to do, go to crates.io, check whether somebody else did the work for you. That's the easiest way to get bindings possible. Just use whatever somebody else has done before and cooperate and help them fix bugs if you encounter any. Brings the entire ecosystem forward, and it saves you a lot of work. If you still need to do it, we have the approach to do it in cargo is build.rs, which is a piece of Rust code that gets compiled at compile time. When cargo sees a build.rs file, it compiles it, it executes it, and this code can interact with whatever, basically do everything you can express in Rust code. Run that, and then return some information back to cargo about when to run the build.rs again and similar things. So it's Rust code. So of course we have crates for that. So the first one is the CC crate, the wonderful crate for whenever you just have a couple of files you need to compile. It basically allows you to drive or run a C and C++ compiler directly. So basically includes the CPP Crate as a developed dev dependency, so it will be available for the build.rs script. Tell it, here, find a compiler, build these 1, 2, 3 files for me, generate a static library out of it will generate a static library out of that, and that can be included in other parts of your project. If it's more complex, you want a more specialized trait. For example, there is a CMake crate, which basically drives the normal CMake configure, build, install process, and then makes the build results available to the cargo project to include in other places. If you need to go the other way and have a little Rust code, like let's say one library or something, and want to integrate it in an existing CMake project, you will need to integrate it in the CMake build system or in the C++ build system. I just assume for now it's CMake, of course, other options. For CMake, there is actually a really good solution we found in Slint. That's the corrosion project, which is basically CMake code to interact with cargo and drive cargo for you. A minimal project looks like this. So the first 2 lines are the boilerplate you have basically in every CMake project. Just telling it the minimum CMake version and what kind of project you use. You tell it, I have a project, it uses a C++ language with languages CXX. You don't need to mention Rust at all, no need. Then you do find package corrosion, which will go and pick up the corrosion you have to have installed separately. There are other ways to actually make CMake download and install it for you at build time if you need that. But this approach here assumes it's installed on your system somewhere in a place that CMake can pick it up. And then all you need to do is basically point it to a cargo toml file, and the corrosion will do the rest for you. So you can, of course, also set features and all the other things that you need to do. But afterwards, you can, the build results of the cargo build project will be available as normal CMake targets, and you can just link to them as with any other CMake target. So that works really well. We use that a lot, basically to enable C++ developers to just interact with our code without needing to know that it's in Rust. So they can ignore that fact away if they want to. Yeah, that's all I wanted to tell you about. Thank you for your attention. This QR code should take you to slides or a copy of the slides with speaker notes and a lot more text, because my slides are a bit sparse. Please feel free to reach out to me, Twitter, whatever. And these are links you will find at the presentation. Thank you for your attention.